Okay, this is the second theorem you need for Möbius transformations, and it's called the intersecting secants theorem. And what I'm going to do here is the same sort of thing as with the intersecting chords theorem. I'm going to take a point Z on the circle. I'm going to take another point A over Z star, defined geometrically as another point on the circle. I'm going to show that that value A is the same wherever Z is. So by doing that, I will show that when Z goes around the circle, A over Z star goes around the circle for a fixed value of A. It doesn't depend on Z. So A over Z star is a circle. So 1 over Z star must go around a circle too. Okay, so here's the pole outside the circle. There's the centre. And I put in a few letters to help me. I will now put in a perpendicular from the centre to this line DF. Call that E. And I'm going to write in that line there. Okay, right. A is equal to the length of OD times the length of OF. Right, okay. That's OE minus DE. Yeah? OD is OE minus DE. And OF is OE plus EF. But EF and DE are exactly the same because this is a circle, that's symmetrical. So I can write DE instead of EF there. That's the difference of two squares, OE squared minus DE squared. Now I do Pythagoras. OE squared is equal to OC squared minus CE squared. DE squared is equal to CD squared, which is the radius of the circle. So I'll just call it R squared. It's the radius minus CE squared again. The CE squareds cancel out, so that's equal to OC squared minus R squared. R is fixed for the circle. OC squared is fixed for the circle. Therefore, A is a fixed quantity wherever Z is on a circle, and A over Z star goes around the same circle as Z does when Z goes around the circle. Therefore, 1 over Z star will go round a circle, not the same one, but it will go round a circle.